I'm going to describe our recreation in JuliaSim of the HL-20 lifting body. The HL-20 was designed in the 90s by NASA as a crew vehicle concept for the space station Freedom. It would eventually evolve into the Sierra Nevada Dream Chaser, which will fly to the ISS later this year. HL-20 is fantastic for our purposes, since NASA prepared extensive documentation on how to simulate it, as shown alongside the finest copy I've written in this report. The vehicle is a classical lifting body, controlled by a combination of body flaps, rudder, and wing flaps. This control scheme is one of the major challenges posed by the vehicle, since it begets a complicated control-to-surface mapping. NASA's documentation includes their control mixer that maps pilot inputs to control surface outputs, but we need to recreate this in JuliaSim. Before I dig into that, let's jump forward to show you what this all looks like. In this demo, I'm going to control the HL-20's control surface deflections using this gamepad. You can see the results of the inputs reflected on the 3D model of the aircraft on the right. I'm initially diving down to build up energy to let us level off. You can see our airspeed on the left of the PFD and the altitude on the right. Once I level off, the airspeed rapidly diminishes in exchange for a near-zero descent rate. Now, I'm going to deploy the spoilers. You can see the body flaps all go up as I use the left trigger to deploy them, and we can see the vehicle responding well in roll if the spoilers deployed. Furthermore, once I put the vehicle into a descent, we can see the airspeed stabilize at a lower value than my earlier dive, showing the effects of the drag brakes on the vehicle's aerodynamics. When I pull the brakes back in, the vehicle picks up a bit more energy and decreases its descent rate. I'm able to use this reduced drag to again pull the aircraft up out of its dive and stabilize it a bit for the end of the demo. We built the HL-20 model by using JuliaSim as glue between components built in JuliaSim, in ModelingToolkit, in a NASA model transfer language, and the native Julia code. Joystick inputs are coming in here, in a block implemented in ModelingToolkit and native Julia, and are then fed through a series of gains to the mixer. The mixer, implemented in JuliaSim itself, takes the user's inputs and translates them into control surface deflections. I'll open this up and dig into the details in a minute. Finally, we use the control surface deflections, like the drag brake commands shown here, to drive a 6-degree of freedom model implemented in ModelingToolkit. We implement our own kinematics, but import the aerodynamic and atmospheric models from NASA interchange format. The 6-degree of freedom then feeds state information back into the mixer, like Mach number, for use in mapping pilot inputs to deflections. This is the HL-20 mixer model, diving into the HL-20 model a little bit more, that converts user inputs that are coming in here into control surface deflections going out here. This model is a little bit daunting, so for this presentation, I'm just going to focus on how one little chunk of it, the elevator or pitch control, is mapped and how that corresponds to the original NASA report. Here's the flow for how the elevator command is mapped through from the joystick to the control surfaces on the vehicle. The elevator command comes in on the left-hand side here and is then limited to between plus minus 30 degrees by this range limiter component here. This output then goes through a first-order filter for both the left and right-hand side elevators, which is then slew rate limited to 20 degrees per second. This output is then range limited yet again, and is then sent out to the actual control surfaces built in as part of the 6-degree of freedom model, including the left and right-hand side actuators. These outputs that we're generating from Mixer are then fed through the top-level model that I showed earlier into the 6-degree of freedom model here. The 6-degree of freedom model, if we look at it in JuliaSim, is empty. There's a big fat nothing here. The reason for this is that this is actually an external component. This is something that's being built in ModelingToolkit itself and then being used from JuliaSim as an external system. Let's then dive into that external 6-degree of freedom model. Jumping into the Julia code that implements it, the 6DOF is just a normal ModelingToolkit component. I'm building up the ultimate 4 kinematic equations by hand here. I'm just writing out the rigid body equations in motion for the vehicle. The rest of the 6DOF system is then largely devoted to interacting with the aerodynamic model. It generates the states used by the aerodynamic model, which then feeds forces and moments back into the 6DOF system. The aerodynamic model was provided as this XML-based DML interchange format. This data includes the aerodynamic lookup tables as well as the equations by which to convert those lookup tables into the forces and moments we need. We ingest this DML format automatically by automatically parsing and generating a ModelingToolkit component out of the XML files. We also ingest and run the test cases included in the DML source models. The other major external component is the joystick input. HL-20's joystick itself is pretty simple. It's just wrapping two different joystick inputs, the other one here is my rudder pedals, and converting their ranges into ones the HL-20 understands. These low-level joystick components are provided by the ModelingToolkit Joysticks library, which uses GLFW to access, via direct input in my case, the state of the hardware. This is then mapped into real-time as a discrete time input that's then transcribed via zero-order hold. To bring this all together, that real-time simulation that I showed is then just normal Julia code running the JuliaSim model in real time. I'm taking the HL-20 model here, stapling a real-time frame limiter provided by the joystick library, and then setting up the PFD and 3D visualizations that I showed earlier. I won't go into too much detail there, but they're implemented in Julia using Mackie. Finally, I go to set up the problem, which is just a normal ODE problem with some initial states and gains to make the aircraft feel right, and then solve it. That's all that's needed for Julia and JuliaSim to compose and simulate this ensemble of many different models and implementation modes. In summary, we use JuliaSim to compose multiple different models and implementation styles into a single real-time aircraft simulation that I could fly off a joystick. This demonstrates both JuliaSim's own capability to build out models, as well as its ability to compose with models built in native Julia, in ModelingToolkit, and even in external modeling languages.